Hi everyone, in this video we'll look at the EM algorithm for Gaussian mixture models. So as discussed earlier, the aim of the Gaussian mixture models is to estimate mu I, sigma I and pi I, where I is from 1 to k. That is, we have to estimate k Gaussian distributions such that the probability distribution for a given point x, the probability density function at a given point x, is a combination of Gaussian distributions, and this is a convex combination of k Gaussian distributions. So to estimate this, we use something called as EM algorithm. So the EM algorithm is as follows. So firstly, you initialize mu I, sigma I and pi I for I is equal to 1 to k, and you can use various kind of heuristics to initialize these values. Once you initialize these values, you calculate something called as responsibilities for every data point. So let's say in our data set we have n data points, x1, x2, xn, and each of these points belong to some dimension, let's say capital L, and we have to calculate responsibilities for every data point, and we'll shortly see that what do we mean by responsibilities. And this is known as E step. And next we have to re-estimate the parameters mu I, sigma I and pi I for I is equal to 1 to k using the responsibilities calculated, and this is known as M step. And we loop through 2 and 3 again and again till we reach convergence, or till we reach the expected amount of computation power which we want to dedicate to our problem. So let's quickly see what do we mean by responsibilities. So to understand the concept of responsibilities, let's say we are calculating responsibility for point xn belonging to our dataset, and let's say we are in 2 dimensions, so xn has 2 dimensions, xn1 and xn2. So responsibility is denoted by r, and we calculate responsibility for each of the k Gaussian mixtures that we want to estimate. So in this case we'll calculate Rn1, Rn2 and Rn3. So responsibility means that how much is the, let's say Rni means how much is the ith Gaussian distribution responsible for generating point xn. So we calculate this responsibility for all the points x1, x2 up to capital Xn, and xn belongs to this set of all the data points that we have. And to calculate the responsibility for a given point n for, let's say, the cluster K or the cluster I, what we do is we first see that we have to calculate that what's the probability that this point xn is coming from the cluster I, and to do that, first we see what is the probability of any point coming from cluster I. That is probability of a point coming from cluster I. And that probability is, as we know, is pi I. Right? Because Px is sigma pi I into normal distribution of x given mu I and variance. So probability of the cluster, ith cluster, a point coming from ith cluster is pi I, because pi I is the weight for this Gaussian distribution, and hence first we will see what is the probability of obtaining the cluster I, and once we have obtained the cluster I, then we will see that what is the probability that we will obtain the nth point from cluster I, and that would be given by the normal distribution of xn given cluster I. So this is the probability that our nth point xn belongs to the cluster I. But to calculate the contribution of the cluster I, we have to normalize this. So contribution of cluster I is nothing but probability of the point coming from cluster I divided by probability of point coming from some cluster j. So we have to normalize that, which means that we calculate probability of this point coming from cluster 1, we calculate probability of this point coming from cluster 2, P2, and probability of this point coming from cluster 3, which is P3, and then the responsibility of cluster 1 is nothing but P1 upon P1 plus P2 plus P3. That's what we are trying to do here. So we calculate the probability of nth point coming from cluster I, and then we add the total probability of obtaining the nth point from cluster 1 to k, and we sum all those probabilities to normalize that. So basically sigma of r of ni, that is what normalization gives us is sigma r of ni for I is equal to 1 to k, that is contribution of kth, sum of the contribution towards point xn by all the mixtures would be 1. So this is known as responsibility. So the each step is to calculate the responsibility for all the data points. So each step is calculate r and I, which is pi I into normal distribution of xn given mu I comma sigma I divided by pi j from j is equal to 1 to k, assuming that we have total k Gaussian distributions which we want to estimate. Normal distribution of xn given mu j and sigma j. And once we calculate the r and I here, next step is m step. So once we calculate these responsibilities, in the m step we update our parameters mu I, sigma I and pi I from I is equal to 1 to k, that is we update the parameters of all the k Gaussian distributions as follows. So mu I becomes, basically we will look at all the data points which belongs to ith cluster, or we can say which contributes to ith Gaussian distribution, and since this is a case of soft assignment, soft assignment means that every data point xn, any general data point xn, belongs to each of the k Gaussian distributions up to a certain extent, and how much it belongs to a particular Gaussian distribution is given by Rn. So it belongs to the first Gaussian distribution by amount Rn1, it belongs to the second Gaussian distribution by amount Rn2, and so on, and it belongs to the last Gaussian distribution with the value of r and k. So basically what we'll do is we'll take the average of all the data points which belong to ith distribution, and let's say we have x1 to x capital N data points, so n is from 1 to n, and since this data point only belongs to ith Gaussian distribution by a factor of r and I, we take the weighted average and we divide by sigma. So if you note that had it been an hard assignment, by hard assignment means every data point belongs to only one of the Gaussian distributions. So what we would have done is we would have taken all those data points which belong to the ith Gaussian distribution, and let's say those data points are y1, y2 up to y capital M. So our mu I would have been simply sigma of yn, where n is equal to 1 to capital M, divided by m. So basically it would have been simply the average of m data points, but now each of the data points x1 to xn belong to the ith Gaussian distribution, but we don't know that how much it belongs to ith Gaussian distribution unless we calculate the values r and I. And once we calculate the values r and I, instead of taking the normal average, we take the weighted average of the data points xn's, where weight is given by r and I. Similarly, we calculate the standard deviation, the variance matrix sigma I, as follows. So we use the mu I calculated before. So basically what we do is we calculate this matrix for each data point, and we take the weighted average of these matrices where weights are given by this r and I. And finally we calculate the updated values of pi I, and pi I is simply ni divided by n. So ni is simply sigma r n I is equal to n is equal to 1 to capital N, that is number of data points belonging to ith Gaussian distribution, and n is simply sigma ni for I is equal to 1 to k, that is total number of data points in our data set. So basically n would be nothing but, since we had n data points, n would be simply equal to this value. So this gives us the probability of obtaining a data point, prior probability of obtaining a data point from ith Gaussian distribution. And why are we calling it prior probability? Because we haven't seen the exact data point xn. So the posterior probability would be, the the probability of xn belonging to ith class would be the prior probability, that is probability of obtaining any data point from ith class, multiplied by, given that we are in the ith class, what is the probability of obtaining nth point. So this would be the prior probability. So these formulas for calculating mu I, sigma I and pi I, the formulas for calculating these have been obtained by using maximum likelihood estimate. So just to quickly recap, what maximum likelihood estimate does is obtain the parameters such that the likelihood of dataset x1, x2, xn is maximized using those parameters. So EM algorithm now simply reduces to initializing mu I, sigma I and pi I, calculating the responsibilities for every data point, basically for x1, x2 up to xn, and then we have to re-estimate the parameters mu I, sigma I, pi I for all the k Gaussian distributions, and to re-estimate the parameters we use maximum likelihood estimation, and we repeat the steps 2 and 3 until convergence. So this gives us mu I, sigma I and pi I, and then we can obtain px for any given x. And let's say we have to decide that how much does this point x belong to each of the clusters. We can decide that using rx1, rx2, that is using the responsibility matrix. And if you have to choose just one cluster to which we want to associate this point with, we can choose the cluster S, which maximizes RXS. Basically, the cluster with maximum responsibility for data point X can be chosen as the cluster for that particular data point X if we want to choose just one cluster.